So you'll remember that enantiomers have the same chemical formula and that the atoms are put together in the same order, only in a different stereochemical sense. So what we have are enantiomers will have identical physical properties. We would expect their melting points, boiling points to be the same. They're going to react chemically the same. They will rotate the plane of polarized light differently. And they'll interact differently with receptors. They'll interact with receptors differently. So here we have R-carbonone and S-carbonone. The R form gives us spearmint, and the S gives us caraway. So when we taste these, we experience two very different chemicals. So I've got the camera facing a flashlight, and I have a sunglass lens. It's a polarizing lens. It's polarizing the light, and it dims the glare a good bit. If I put a second one on top, there's not a big change, but if I rotate the one on top, the light will just about go off. All I'm doing is rotating the lens. Okay, so the way they did these experiments is they polarized light, and then they put a solution in front of the light that was able to turn it, and they saw a decrease in the amount of light coming through. And our optically active organic compounds are actually able to turn light in much the same way that the second lens does. So this is a diagram of what we were just looking at. Here we have light that's normally oriented in a random fashion. It passes through a polarized filter. That's my first lens. And this only allows photons in a particular polarization to pass through. If the second filter is arranged in the same orientation as the first, the light will pass through and the person sees it. If one filter is turned, however, so this one's going up and down and this one's going across, no light will pass through. So polarimetry was discovered in 1815, and it was discovered that some organic compounds could rotate light. These substances were optically active. A polarimeter is what we use to measure this rotation. And it's going to look a lot like a spectrophotometer. We have ordinary light coming in here, a polarizing filter that orients the light so it's all in one direction. This is a sample tube where we'll put our organic compound. It rotates the light. When it comes out, it's in a different orientation, and that can be detected by the analyzing prism. Chiral compounds will rotate polarized light. The observed rotation is dependent on concentration and path length. So if I doubled the concentration, I would have doubled the observed rotation. If I make the path length shorter, then I'll have less rotation. So specific rotation is denoted like that, and it's the rotation of 1 gram per milliliter with a path length of 10 centimeters. And we can calculate it. This is our specific rotation, is calculated as the observed rotation divided by the concentration in grams per milliliter and the path length in decimeters. The specific rotation is also dependent on temperature and wavelength. And so we report it as brackets, the number of the amount of rotation is degrees, temperature at top, wavelength at the bottom. Light can be rotated to the right, which is the positive direction, or to the left, which is the negative direction. You cannot use the R and S configurations to predict whether the rotation will be positive or negative. It would be nice if you could do that, but you can't. Here, R bromobutane is negative, and S 2-bromobutane is positive. So we can do some calculations here. If we're given 0.575 grams of MSG and it's dissolved in 10 milliliters of water and placed in a sample cell 10 centimeters in length, the observed rotation at 20 degrees C using the D line of sodium is 1.47. Calculate the specific rotation of MSG. So the specific rotation is equal to the observed rotation divided by the concentration and length of the path. Okay, so the observed rotation is right here, 1.47. The concentration is given to us here. We've got 0.575 grams in 10 milliliters. And these are the right units. We want our concentration to be in grams per milliliter. And our path length is given in centimeters, but we can quickly calculate that that is 1 decimeter. And we get a positive rotation of 25.6. And that would be a figure that is look-upable. Okay, so a couple terminologies. If we have an optically pure solution, it will only have 1 enantiomer. If we have a racemic mixture, we have both enantiomers, and this will be optically inactive. Optically inactive. That's because what one takes away, the other gives. So if one molecule makes it turn right, the next molecule makes it turn left, and we're back where we started. Sometimes when we have reactions, we'll produce an enantiomeric excess. We'll have more of one. So we have both enantiomers, but we have them in unequal amounts. Both enantiomers, but unequal. And this will be optically active. This is calculated. We do the rotation observed divided by the rotation of a pure NaN meter. So if we have a problem like this, we have the specific rotation of L-DOPA in water is minus 39.5. A chemist prepares a mixture with its enantiomer, and the mixture has a rotation of minus 37. Calculate the percent EE of that. So percent E. Enantiomeric excess. We want to put the observed on top, and in this case it's minus 37. And we'll put the literature value on the bottom, which was minus 39.5, and we'll get 94%. And that gives us an idea of how pure our mixture is.